Greetings. Thanks for the opportunity to tell you all about launch vehicles in this Pathways to Space class. Space is an increasingly important part of our daily life, and nothing gets there without a rocket ride. Now, I know you have a party to go to this weekend, and I'm sure you want to impress your friends by telling them that you are a rocket scientist. Our goal here is to give you some great ideas to pull that off. My name is Dave Murrow, and I've been working on NASA missions for nearly 30 years. I studied engineering here at CU and went on to work for NASA and our aerospace industry designing, launching, and flying space missions. The best part about rockets is what Hollywood calls special effects, we call fire out the back end, and really is just a controlled explosion. So take a look at this explosion. Lots of energy is released in a very short time by adding a spark to some fuel. In geek speak, we call that a transformation from potential or stored energy to kinetic energy. So stuff really moves in an explosion. Now, imagine that explosion is magically wrapped up in a tube with a cap on one end. Remember that your magic wrapping has to be very, very strong so the explosion doesn't escape out the sides. All of that energy is now pointed in one direction. What do you suppose will happen? That's right, the tube will shoot off in the direction of the closed end. And there you have it, the simplest of rockets. In reality, of course, you don't cause the explosion and then wrap it up while it's happening. You wrap up an explosive material. And then, after standing back safely, you ignite it. Like this. Or this. Or this. But not this. More like this.
7, 6, start, 2, 1, booster ignition.
Okay, so now we figured out how to direct explosive energy to push us around. How does that help us get to space? Well, first, let's agree on what we mean by space. Space is above the Earth's atmosphere. So the rocket or launch vehicle must have enough power to send something, the payload, up above the atmosphere. You can get to space by going straight up and falling back down to Earth. This is called suborbital, and that's the way that Virgin Galactic will someday take tourists to space. Most space missions, however, want to stay longer than a few minutes. As you know, a payload stays in space by orbiting around the Earth. Using my toys, I'll show you again. Like the suborbital payload, it's continually falling back down towards the Earth due to gravity's pull. However, an orbital payload is also moving sideways so fast that by the time it falls, it misses the Earth. In the lowest stable orbit, this is around 17,500 miles per hour. No small amount of speed. The rocket must also give it some sideways speed so that it doesn't come straight back down. The sideways speed is provided as soon as the launch vehicle clears the vertical launch tower and begins by steering the rocket in the direction that us geeks call downrange. The payload is safely in orbit once it has the proper combination of altitude and velocity. So we need to control that explosive energy with a machine that also has to carefully steer both up and sideways. So how do you make a rocket that does this and not this? There's a few key areas that challenge the rocket scientist. In no particular order, they are the engine, the structure, stages, the brains, guidance, and steering, and the payload. First, let's talk about the engine. This is where the explosion occurs. Now, in a car engine, thousands of tiny explosions burn your gasoline, and they're timed to push the cylinders up and down. In a rocket engine, propellant is pushed at high pressure into a combustion chamber, burned continuously, and the exhaust is pointed through a cone-shaped nozzle to direct the force of the explosion. Most engines can be stopped and started in different parts of the flight. They contain pumps and valves and materials that must withstand very high temperatures. Some of the reasons for rocket failures are in these components and are burn-throughs, cracked turbofans, faulty valves, or pressure control regulators. Talk about a faulty turbofan at your party, everybody will rally around you. Just like a car engine, different engines have different characteristics. Some burn fast, and some have high thrust to get the rocket off the ground quickly. Some are much more fuel efficient and better suited to pushing the rocket when it's higher up and already moving towards orbit. And just like there are different types and grades of gasoline, there are different types of propellant. A key difference from that car on Earth is that a rocket has to bring its own oxygen. Oxygen being necessary for all fires or combustion. So two liquids, called the fuel and the oxidizer, are combined and burned together. Some of them are stored at room temperature. Some are very cold and take very large tanks, but are very efficient. And they all burn much, much faster. Which brings us to the rocket body, or the structure of the rocket. The structure contains tanks inside here to hold the propellant. At the bottom, it holds the engine and all the machinery, and the skin supports the upper stages of the rocket, and the payload is on top. I'll talk more about stages in a minute. The structure has to be very, very light, but also very strong. It has to be light so that the energy of the engine can lift it. And of course, it has to be strong to contain the propellant and support the payload up on top. And of course, it has to support its own weight while on the launch pad. A typical rocket stage will be about 85% propellant mass and 15% structure mass. The structure also has to be strong enough to withstand the tremendous vibration and acceleration during launch. So exotic metal alloys, such as aluminum, lithium, titanium, plus carbon fiber composites, are all used in different parts of the rocket body. Speaking of carbon fiber, propellants, and structure, I need to take a slight detour and talk about solid motors, or solids. A solid, like the picture of our matchstick rocket earlier, is a self-contained rocket with little or no smarts. A cork-like flammable material is packed into a lightweight case like this, made of either carbon fiber or very thin metal with a special nozzle on the bottom. When it ignited, the solid propellant just burns until it's gone. A solid is very efficient and can be used to add more thrust for launch, like these boosters, or as the final stage for a rocket to give the payload its final push. The last piece of the structure to mention is the shroud, or the fairing. The lightweight shell on top of the rocket protects the payload from air friction as it climbs through the atmosphere. After the vehicle is safely through the thick parts of the atmosphere, the halves of the fairing are split apart and pushed away from the rocket and fall back to the Earth. Which brings us to the idea of rocket stages, or parts. Basically, the idea is to drop off the parts of the rocket that you're done with as it flies further up and up. There are really two kinds of things that you'd like to ditch as you ascend. Remember that higher thrust is needed at liftoff compared to later on in the flight. So your really beefy liftoff engines, like those solids, can be dropped off when you're done with them. Also, carrying a large propellant tank after it's empty, like the Space Shuttle external tank, just reduces the final mass to orbit, so the tankage can be jettisoned. So for efficiency, the rocket's designed and built in parts called stages, which are used and dropped off when spent. Most launch vehicles contain either 2 or 3 stages, depending on the needs of the payload or the spacecraft mission. For example, this rocket I keep showing you here was used to propel a spacecraft towards a comet and contains booster solids plus 3 stages. First stage here, second stage is here, and third stage is up hidden by the fairing. So, let me tell you a quick word about vehicle reuse. I talked about things getting spent, but why not just reuse something? So the space shuttle, because it brought the engines back with it as part of the space shuttle orbiter, reused those engines. Also, the big solid rocket motors were reused after being recovered from the ocean. Currently, both SpaceX and Blue Origin include reuse of components as a major part of their design. The first stage booster flies back to a safe landing spot for reuse. This technique replaces new first stage builds with refurbished first stage to save on cost. However, the first stage rocket must reserve some of the fuel for landing, so it's jettisoned before it's empty, and it has to be guided back to the launch site. Now, let's talk about the launch vehicle payload, also known as the spacecraft. The spacecraft, designed for its unique mission, must fit into the shroud and must not weigh more than the launch vehicle can carry. Along with surviving the launch vibration, these are the primary constraints on the spacecraft design. Spacecraft and launch vehicles have evolved together since the 1950s. Currently, there are usually one or more launch vehicles that can work for a spacecraft mission, and launch vehicle selection is one of the early design choices of the spacecraft designer. In the case of a new rocket design, typically a class of spacecraft sizes and missions, like COMSAT missions, would drive the design. All of which brings us to launch vehicle sizes. A large or highly capable spacecraft will obviously require a larger launch vehicle. Similarly, a spacecraft mission going further from the Earth to Mars or Jupiter will also require a larger launch vehicle. For example, a low Earth orbiting mission may launch on this vehicle, the Atlas 400, made by United Launch Alliance, or the SpaceX Falcon 9. A larger spacecraft may select a larger variety of Atlas, such as this one with 5 solids, or this Delta rocket with 3 liquid cores. Soon, SpaceX will deploy its Falcon 9 Heavy, and Blue Origin its New Glenn reusable vehicle. Even larger missions, such as those carrying astronauts to the Orion spacecraft, will require the largest rocket ever built, NASA's Space Launch System, or SLS. Wow, so that was a pretty whirlwind tour of all of the launch vehicle design ideas. One more concept, and you'll be ready to entertain at that party. So, different space missions have different orbits. Some are geostationary, that is, they hover over a spot on the equator. Others move from north to south at a lower altitude, and the Earth rotates underneath them. Others go to the moon or leave the Earth's orbit entirely. How does a launch vehicle satisfy all of those different needs? Well, the answer really has 2 parts. First, the launch site, and then the launch direction. First off, where you launch from has a lot to do with your possible destination. If you launch due east from the equator, for example, as you fall back to the Earth in your orbit, you'll stay in that equatorial plane over the equator in what's called an equatorial orbit. However, if you launch due east from, say, Cape Canaveral in Florida, or even more so from up here in Russia, the gravity from the center of the Earth will pull you south. Your orbit will then cross the equator, head further south, and when it's south, it will be pulled back to the north. This orbit, at an angle to the Earth's equatorial plane, is called inclined. Now, suppose you launch from Cape Canaveral towards the northeast. So here we are in Florida. We can't launch straight north, or the stages would fall back on New York City. That would not be good. But if we launch to the northeast over the ocean here, we'll go a little higher, further north, before we get pulled back towards the south. We'll wind up overshooting the equator. Again, in geek speak, that orbit is more inclined, which is exactly what you want to do if you launch to the International Space Station. So the orbit you end up in is determined by both the launch site and the launch direction. As a launch vehicle mission designer, your payload will ask you for delivery to an orbit, and with a well-designed vehicle and a well-chosen launch site, you can provide exactly what's needed. Okay, now you know how a launch vehicle fits on the pathway to space. Now it's your turn. Get out there. Not to class. Get out there to the toy store and buy a water rocket. Get out there to the hobby shop and buy some Estes rockets. Whatever you do, get out there and make something fly.